All right, so in this module, we are going to dig around into organic molecules, pigments, and dyes. And we're going to start with pigments first, and then we're going to talk about organic molecules and then dyes. Before we get started, I want to define a few things for us. And one of the things I want to define is colorants. Now, colorants are just substances that impart color. Okay, and in this screencast, we're going to talk about kind of three different substances that impart color. The first one are pigments. These are generally insoluble in water or organic solvents. Now, we're going to talk more about organic solvents in Module 10, but these are things like oils. So if you think about oil paintings, right? And for us, these things are the things that contain metals. A lot of times they're referred to as inorganic compounds. But the big thing here for us is that these guys are going to be ionic, right? And they also require a binder to hold them to the substrate. Now, and so I have a picture here of some just pigments, and that's the first thing we're going to talk about in this screencast. Now, we're also going to talk about dyes, and you may be familiar with dyes. This is like blue food coloring is shown here, and that's an example of a dye. Dyes are soluble in water or organic solvents, like that oil again, right? These things tend to be nonmetals, and so from way back in Module 5, right, we know that this means they're have covalent bonds, okay? Now, we can also have lakes, and what we do with lakes is we take one of those soluble organic dyes and it's attached to an inert, right, support. Okay, and that inert support, what that means is that's non-reactive, and it also makes this now insoluble. So basically, when we talk about lakes, it's dyes that have a lot of the same properties as pigments because now they're insoluble. Now, the support itself, right, is usually semi-opaque, right? It's also usually white. And so some examples of this include a barium sulfate or aluminum oxide. Now, one of the things I wanted to show you was what happens when we put pigments, for example, or dye stuffs into different mediums. And so, for example, this is a dry pigment, and it's added to watercolor, and it doesn't dissolve. It's suspended in it, and so you can see this here. And then you can also see it in linseed oil and also a glaze here. And so you can see how what the pigment suspended in changes the color itself, right? It changes the color, like the shade or the tone of the color. Now, on the rest of the screencast, are just going to talk about pigments. So we've got some ideal properties of pigments. And the first ideal property is we want it to be light fast. And what I mean by that is we want it to resist fading. Okay? If we put it in the sun, we don't want it to fade. Okay? We want it to be chemically inert. We don't want it to react with other things. So we want it to resist oxidation. Right? It does not undergo any chemical reactions. with other pigments or binders or grounds, right, which is the base of a painting, or pollutants. Okay, so you wouldn't want to paint a pigment on a painting and then it react with another pigment or that you've painted next to it and give you a different color. Okay, you want it to resist bleeding, and so you want it to be as insoluble as possible so that it will not migrate through the binder to other paint layers. Right. And then you want there to be uniform particles. You want this for a few reasons. One is you want it to so that it'll be easily dispersed in the binder. But then you also want it to be uniform particles because there is color variation with particle size, okay? And then you want it to have high opacity. And when we're talking about this is you want it to have high hiding power, right? So you want it to cover well, cover your surface well. Now, before the Industrial Revolution really began, early pigments were ground colored minerals like iron oxide. And so I have this chart here for you, and you can see here kind of historically, we've got cave paintings, here's Egypt, here's Pompeii, here's the Renaissance era, and then here's Impressionist. Okay, so we've got a range of time. And what you're going to see here are these early pigments are ground, right, colored materials. Right, and so if we think back to one of our first labs, right, we messed around with ochre, and this is an iron oxide. Now, after the Industrial Revolution, then synthetic pigments really picked up, like Prussian blue, which we're going to talk about, and those were developed. And that was really followed rapidly with the development of a lot of kind of synthetic pigments like ultramarine, cobalt blue, cadmium red. There's cadmium yellow and a chrome oxide green. Now, commercial synthesis began approximately in the 19th century, and these are generally prepared by a precipitation reaction. So my hope is that when you're listening to this, you have already made Prussian blue in lab, and you've seen that this occurs through a precipitation reaction. And so this was a huge kind of revelation or revolution in pigments because these were really brilliant colors. They were light fast, they were heat stable, and they had high tinting powers. So let's dig around into a few of the pigments kind of at the beginning here. And so when we first started this class, we talked about the Lascaux cave paintings, and these ancient pigments were used to color the caves. You can see here. These were ground colored materials, lots of iron oxide. I want you to notice that these are browns and blacks and reds. They did have a green pigment at the time, but they didn't really use it, which is kind of interesting. And so what the scientists did is they took a sample from the snout of the great bull, and what they found was that the black pigment from the snout of the great bull was haussmannite. Now, this is a big deal for a couple reasons. One is Most of the time when we have black pigments, they are carbon based. And so they were really expecting this to be kind of a carbon based pigment. So they were really surprised by this. Now, hossomite itself is a manganese oxide. And right, there was no local source of this manganese oxide at the time. This can be made by artificially heating rocks that are rich in manganese, but the process requires temperatures of around 1650. It's possible that the hossomite came from the Pyrenees Mountains, which were approximately 150 miles away. We don't know how this pigment got from the Pyrenees Mountains to the cave, but it does indicate that the fact that it traveled, that paint had value and was carried a long way. And so that's one of the more interesting pigments that we find in kind of like 10,000 BC, kind of that ancient culture. Now, another really interesting pigment that we find is Egyptian blue. This is really considered to be the first synthetic pigment. Right, and it was developed around 2200 BC, about the time the Great Pyramids were built. It's made from ground limestone mixed with sand and copper-containing minerals like azurite or malachite, which is then heated between 1470 and 1650. So it's made by heating copper-containing minerals to approximately 1470 to 1650 degrees Fahrenheit. And what this resulted in was an opaque blue glass that was then crushed to make the pigment. And it was combined with thickening agents like egg whites, which we've used in lab, to create really long-lasting paints and glazes. You can see this is kind of a representation of it here. You can see how it was painted here. This is King Tut's tomb. You can see there are baboons here that were painted blue, and this was all done with Egyptian blue as well. It was used all the way until the Roman times, and then basically it was forgotten. And then scientists figured out how to remake it again in the 19th century, but by that time there were easier ways to make blue because this is a super finicky process. Now, where I find this to be really interesting is we talked in the color chapter about color influencing language. And so I put this link here for you. And when we talk about color influencing language, one of the things we know about ancient languages is that the first two words that you got for color were generally black and white. And then after that, the next word that was developed in ancient languages was red, right? The color of blood. And then yellow and green. There's a lot of ancient languages that don't have a word for blue. However, ancient Egyptian language does. And there's a hypothesis that the reason they had a word for blue is because they were able to make this blue pigment. So I find that to be really interesting. You can read about it here, which is really neat. Another blue pigment that was used pretty frequently, particularly in kind of the Renaissance era, was ultramarine, which is made from a semi-precious stone called lapis lazuli. So lapis lazuli is a semi-precious stone. Right? And it gives a really beautifully intense color. So when it was honestly one of the finest and most expensive blues used by Renaissance painters. Right? By Renaissance painters. So let's put it in. And so if you, in the Renaissance time, if you looked at a painting and it had this kind of really pretty rich blue, you knew that it was ultramarine, which was made from this semi-precious stone. And so you knew that that was a really expensive piece of artwork. It would be kind of like if they saw gold foil on a painting, they knew it was a really expensive piece of artwork. It was often used on the robe for the robes of the Virgin Mary, and symbolized holiness and humility. It remained an extremely expensive pigment until people figured out how to synthesize it in about 1826. So it was made synthetically in 1826. So here are two paintings that used it. This is a painting titled The Blessed Virgin Mary. This was painted in approximately 1654 by Sassoferrato, I think how you say it. Right? And her blue cloak here is painted in ultramarine. And then this is the turban of the girl with the pearl earring, right, made by Vermeer. And that turban, the blue turban there, is painted with a mixture of ultramarine and lead white with a thin glaze of pure ultramarine over it to kind of give that that sheen there. Now, when ultramarine blue was made in Renaissance time, it was a long process. So they had to take a chunk of lapis lazuli, and they pounded it with a bronze mortar. So they took a chunk of lapis lazuli and they pounded with a bronze mortar, like a mortar and pestle, if you've seen that. It took a really long time to do this because it was a rock, and they also covered it up so the dust didn't float away. They then put it on a slab and continued to kind of pound and sieve and pound to get a really fine particle size. Then they melted pine resin, right, gum mastic, and wax in with that blue, right? And they strained it with a linen cloth and basically made a dough out of it. They greased their hands with linseed oil and made their hands really, really slippery, and worked with the dough for, it's a, like my reference says, every day for 3 nights and 3 days. Then they poured the water into ashes to make a lye and put the dough in the bowl. And when it was saturated, they drained it into a glass bowl and continued to add more lye and repeat. And then they let the lye evaporate away, or the water evaporate away, and then they had a blue powder. This was a really, really long process. For a long time, it was done in monasteries, and so people thought that only men worked with this. But recently, within the last several years, they uncovered a skeleton of a nun who had kind of some grains of this lapis lazuli or ultramarine in her tartar of her teeth. And so that indicated that that women were also allowed to work with it as well. And so I'll try to post that on our Canvas page so that you can read about that. But that's a really kind of interesting historical note as far as pigments were concerned. So we're still kind of hanging out here in blue. I want to talk to you a little bit about Prussian blue. Now, Prussian blue was probably synthesized the first time by a paint maker named Johann Diesbach, right, in Berlin. Around the year 1703, what he basically did is he was trying to make red paint, and so he was using a dried beetle, which is a cochineal beetle, right? Iron sulfate and potash. Now, potash is used as a mordant, and mordants just really help dyes stick to fabrics or stick to things. Okay. Now, when he was making this red dye, he waited to the last minute and didn't have any potash. And so the only potash he could find was outside of Busher. It was tainted with blood. And he was really surprised when he mixed it in with a dry cochineal, and instead of it making a really pretty red pigment, it made this kind of really deep, brilliant blue. Prussian blue is used in paints. You can see here, this is the big wave, which is a really famous painting. It's used in blueprints, so it's historically been used in blueprints. And it was also used by Van Gogh in like Starry Night. Now, so it's the traditional blue in blueprints. In medicine, right? Prussian blue is used as an antidote for heavy metal poisoning. So it'll complex the heavy metals out, like, for example, cesium or thallium. It's also a common stain used by pathologists to determine the presence of iron in biopsy specimens like bone marrow samples. We will synthesize this in lab. It's really quick to synthesize, and then of course we'll paint a painting with it. So the next group of pigments we're going to look at are the red pigments. And the first one we're going to talk about is cinnabar. Now, you may have seen cinnabar in like vases that look like this. But cinnabar has also been traditionally used as a paint pigment as well. When fighters or gladiators won a fight in the Colosseum in Rome, they would be painted with the cinnabar paint and then paraded through the streets. Now, this cinnabar paint is a really bright, shiny, orangey red mineral that is extracted from the mercury mine in Almaden in central Spain. So the pigment itself is mercury sulfide, right? And it's extracted from the mercury mine in Almaden, Spain. Just a couple years of breathing the mercury fumes, working in the mine would cause a really slow and painful death. So it was a really beautiful pigment, but also very deadly. And it's one of there are several pigments we're going to talk about that are really deadly. Now, the Romans knew how to make cinnabar synthetically, and when it's synthetic, it's called vermilion. And so this is synthetic cinnabar, right? However, it still required the mercury from almandine, and it's still mercury sulfide. Now, artists used this vermilion until the 19th century. Um, and a lot of times when I talk about paints and pigments, I talk a lot about kind of Europe, but I want to point out that the ancient Chinese knew about vermilion 2,000 years before the Romans did. And so they had developed a way to synthesize mercury sulfide vermilion, and you can, and they used it. They would grind it into a paste and use it as the ink for official seals. This is a piece of artwork called The Night Shining White by Han Gain. So this is Night Shining White by, right? And Night Shining White was the favorite horse of the Chinese Emperor Zunzong, right? So let me spell that. So he had him paint it. All the red vermilion ink stamps that are shown around here, so these are all the red vermilion, are made by people who admired the painting, and a lot of these are the seals of emperors who owned it over the centuries. You can also see the marks here. These were poems. Now, another really kind of red color that was around historically was minium. This is a really bright orange red color. The Romans used it. For writing initial letters or titles in their book. It was really nice. It showed up even on gold or marble. It was also used for inscriptions. Now, the other name for this, so this is also known as red lead, okay? And it's a lead-based paint. It's got an interesting structure. It's got lead. There are two of them with the 2+ state, and then there's one lead with the 4+ state, and then 4 oxygens to balance that out. So this is a time where we see that we've got these two metals and they have different oxidation states. And when I talk about different oxidation states, I'm just saying these numbers here, their charges are different. One is 2+ and one is 4+. And so one of the things that red lead was really used for was it was used by medieval illuminators. Now, an illuminated manuscript were religious manuscripts that were written in medieval times, and the illuminators were the ones who wrote it. And so they would keep it for lettering. And so a lot of times, like when we have like red letter text in Bibles nowadays, right, they would also do that as well. They would also use the red for like holy days. And so if we talk about something being a red letter day, that's where that comes from. But this is all that red lead that is shown here. This is a page from a German Psalter, and so that's what we're looking at. Artists also used minium for bright clothes and to outline halos as well. So it shows up in a lot of those medieval manuscripts. Now, let's talk. So we talked about red. Let's talk about green. We're going to talk about two different greens. One is green earth, which is also known as terre verte, right? Or Verona green. Okay. It's an inorganic pigment. It's derived from a couple different minerals, and it has really a complex formula. It's a potassium with aluminum, right? And iron 3+. And then it also has magnesium in it, and then it's got a silica in it with complex with oxygen. So it's made up of two minerals, particularly the selidanite and glauconite. Okay. Now, terre verte was super easy to process and widely available, but many early artists were really apathetic towards it because it is kind of this dull green. And so, like, this is that kind of green color here. I like this painting because it has kind of this dull green back here. That's green earth, whereas malachite is this richer green. So artists were pretty like, it was available at the time of cave paintings, but it wasn't really used. However, it did get quite a bit of use in the mid 1300s. So in 1351, there was an Italian artist whose name is here, and he wrote the really first Western book of how-to for artists. You know, he was like, okay, if you want to make this paint, this is what you do. Okay. And so in this book, he covered how to get flesh tones by using green earth as the base layer. And so the idea with flesh tones, right, is a lot of flesh tones are pink, but it's understated pink or desaturated. So green is a cross on the color wheel. And so he would start with green and then add the red, and it was more realistic flesh color than a lot of other things. Now, with that green, though, the problem is that the red was not very light fast, and so the red left. And so now if you look at medieval portraits, everybody kind of looks sickly or dead, right? Because the green stayed and the red went away. And so that's just kind of interesting. Another thing that another group that this book is really popular with are forgers, because he has outlined kind of all the ancient arts. People who are doing forgeries can also look and see how things were made in the 1300s and reproduce it and pass off what they do as forgeries. So it's super interesting as far as that is concerned. Now, malachite is a bright green, right? And it's made from the mineral malachite, which is a copper carbonate hydroxide. Okay. And it's a super popular green with creating manuscripts and medieval paintings in Europe and Asia. It's still used specifically in Japan. It's also probably the oldest known green pigment that occurs in Egyptian tomb paintings. So this was around in Egyptian tomb paintings. Egyptians also used it as eyeshadow to help protect their eyelids against getting sunburned. A lot of times it's referred to as basic copper carbonate. And I'm trying to think if there's anything else that I wanted to say. And again, it's just this really nice kind of bright green that we see there. Our next pigment is also a green. It's called Shell's green or emerald green. It was invented in 1775 by the Swedish chemist Carl Wilhelm Schell, right? It was a really deep green. It was reminiscent of emerald, so a lot of times it's called emerald green, and it became really popular for patterned wallpaper, right? It was used in children's bedrooms. It was used for carpets, right? It was used to dye clothing, right? It was used to dye artificial flowers. It was even sometimes used as a food coloring, but it had a big problem. It was copper arsenate. Which has the formula CuHASO3, right? And it is super toxic. Okay. It was not, and he knew when he developed it that it had arsenic in it, and it was really toxic. But kind of in this time frame, there were a lot of products with arsenic, and there weren't great controls, and so it was unfortunately kind of an accepted risk at the time. And so what would happen is people who had this as their wallpaper would die, right, from arsenic poisoning. People who ate the food with it as a food coloring would also die, or people who wore the clothing. Now, in 1815, Napoleon was sent to the island of St. Helena after his defeat at Waterloo, and he died, which what they thought was stomach cancer 6 years later. Okay, and he was buried. Now, in 1840, his body was exhumed and found to be very well preserved, which was an early indication or a symptom of arsenic poisoning. So there was a sample of his hair, and they tested it in the 20th century and confirmed that he had very high levels of arsenic. And so it was discovered in the 1980s that his room in St. Helena had the green wallpaper. So somebody had some of the wallpaper, and they realized that, and they tested it, and of course it was the Shell's green or the emerald green. And so there was then a big rumor that spread that the British poisoned him by using this kind of green wallpaper, which everybody sort of knew was very dangerous. For whatever reason, it is not necessarily illegal to use this anymore, but people just tend not to use it because it is quite so toxic. Or they have come up with other ways to make green and still call it this, like Shell's green or emerald green, but it doesn't have arsenic in it. Let's talk about another toxic substance that was used as paint. And one of these is lead white. Now, this a lot of times was called basic lead carbonate. Okay, and it was 2PbCO3 times PbOH2. So it's lead carbonate with lead hydroxide. Okay, now, beginning in ancient Greece, it was made by putting thin shavings of lead over a bowl of vinegar, right? And those acid fumes would cause a chemical reaction and leave a deposit of white lead carbonate. Now, in the 17th century, a new process was invented in Holland where one pot containing lead was stacked on another pot containing vinegar, and then horse or cow manure was heaped over the pots, and it was left in a sealed shed for 30 days, which I'm sure smelled lovely. Then the manure, basically what it did is it provided the heat to evaporate the acid and carbon dioxide to transform lead acetate into this basic lead carbonate. White lead has been just really the principal white pigment in classical oil paintings, in European oil paintings. It had an absolute beautiful sheen, right? However, it does darken over time because it reacts with hydrogen sulfide in the air, and it produces lead sulfide when it does it. So the lead carbonate, the lead part reacts with the hydrogen sulfide in the air, and it will turn a gray-black color. And so it's why, if you go and look at some Renaissance paintings, the whites don't look like a bright white anymore. They may look more like a gray. And so it was a beautiful pigment to use, but it had some problems. It was toxic, right? And it did eventually react with kind of what was in the air. Now, it was also used in the 16th century as a cosmetic, right? It was used as a skin whitener. It was in really great demand and considered the best available at the time. It caused lead poisoning, right? Damaging the skin, and it caused hair loss. Usage over an extended period of time could cause death. A notable user was Elizabeth I of England. And even as late as the 1870s, a U.S. cosmetics company was using lead in their cosmetic Lard's Bloom of Youth Makeup Foundation, and that was the Lard's company. So it was the Lard's company in the U.S. Lead white was banned in 1977. And so one of the reasons it was banned is because people were painting houses with it, and lead acetate tends to be taste sweet, and so kids were eating it, and lead lowers IQ levels. There were a lot of big studies on that. And so it was banned in 1977. Now, today, most artists use titanium dioxide. It's TiO2. This is a synthetic white made from a metal that wasn't discovered until the end of the 18th century. So this is one of the ways that we detect forgeries. Because if someone is trying to pass off a painting, that happened in the 1600s, and you can test for titanium dioxide, and titanium dioxide's present, then we know that it at least was made at the end of the 18th century, right? So it is used to test for forgeries. We are also pretty familiar with this because it's used in whiteout. So it has really great covering power for us. So I paused there for a second because the image that I wanted did not come through here, but I wanted to put up a few of the Vincent van Gogh paintings here. And so if you have a moment, look up Irises by Vincent van Gogh, or look up any of his sunflowers, okay? And the yellow that you see in those paintings is chrome yellow. This is a yellow that is a lead chromate, right? And when we talk about this, it was discovered in 1762 in Siberia. And it was first kind of used in 1797. A chemist whose name was Louis Nicholas Vauquelin, he basically figured out that this had an element that nobody had used before, right, or discovered. And he called it chromium, right? So the discovery of the pigment led to the discovery of the element name, and that's the Greek word for color. Right? A lot of times these pigments are, so it depends on its acidity, what color you get. So sometimes these pigments can be a deep yellow lemon color, they can be a bright orange pigment. They're a lot of times called chrome yellow or chrome orange. These were used for school buses. So this was used to paint school buses in the 20th century. Um, and so, but the kind of big thing that it was used for that I think we can recognize is that Vincent van Gogh loved it. He painted his sunflowers with it. He just thought it gave a really beautiful yellow color. Now, Van Gogh, right, did have some psychotic episodes, and in one of them, he was apparently found with his mouth full of chrome yellow paint after he squeezed it in straight from the tube. So, chrome yellow is extremely toxic because it's got that lead. And so, it could not have helped his mental condition. And so I don't want to necessarily make the jump that maybe he had a lot of issues because of the toxic paints he works with, but I don't think it's something that we can rule out either. So it is something to kind of consider there. But you're going to hear a whole host of things about chrome. Then kind of the last few things we're going to get to are black pigments and fillers. Most black pigments and fillers are carbon-based. There's a few good exceptions. One is Mars Black, which is named after the god of war, the Greek god of war Mars. Right? And it's an iron compound. But again, most black pigments and fillers are black. Now, there still are some controversies around black pigments. One of those has recently occurred is about the blackest black. That's based on Anish Kapoor. And this is called Vanta Black. And when Vanta Black, which is made of carbon nanotubes, was discovered, it was kind of touted as, hey, it's the blackest black, right? And so the idea here is that, so you can kind of see like it so black, it absorbs so much of the light that it kind of looks like this figurine is now kind of a black hole. And so a lot of artists got really mad about it. And I love kind of this timeline because all other artists were turned away. He's the only one that can use it. And so a guy named Stuart Simple got really, really mad about it and made his own black, which he calls Black 2.0. You can see here in Black 3.0. And I have some Black 3.0 that I hope to bring. And you can see how it's compared to the other blacks. They look gray. So Stuart Simple also released the Pinkest Pink and shares it with everybody, but you cannot be Anish Kapoor, right? And so that's kind of what he says on his website is everybody can use it except Kapoor. And Kapoor gets his hands on it, and he posts his reaction on Instagram by dipping his middle finger in it. And so, right, and it goes on, and it's still a big kind of a fight that's happening about artists and should every artist be able to use the pigments, as well as that. And we'll talk a little bit more about this in class. But pigment history, I think, of course, is really interesting. A lot of the pigments themselves, of course, are toxic. But people are still trying to develop pigments as we go along. And there has been a blue pigment that's been discovered recently that is a new blue pigment. And so, like I said, we'll talk about this a little bit more in class. In the next screencast, we're going to start delving into dyes. Remember, most of the dyes are not going to have metals. They're covalent compounds. And so to understand those, we really need to understand a little bit about organic chemistry. And so in the next screencast, we're going to talk about organic chemistry.